Welcome to PDMA Corporation, home of the MC Emacs. I'd like to thank you for joining us as we continue along in our module presentation discussing the benefits of the MC Emacs and utilizing the 6 fault zone approach to analyzing your electric motors. Today specifically we're going to focus on the rotor fault zone. Now, as I mentioned earlier, we use the 6 fault zone approach to analyzing your electric motors, and those are power quality, power circuit, insulation, rotor, air gap, and stator. And today specifically we're going to focus on our rotor fault zone. Now, if you've listened to me in previous modules, you'll know we discussed the EPRI GE study, in which essentially 10% of your motor failures can be attributed to rotor bar problems. So regardless of the type of motor, the open bar design or cast aluminum design, MC Emacs with the MCE and Emacs uses comprehensive data to determine the severity of the rotor condition, and we can trend that information over time. And our job obviously is to alert you to the condition as it occurs, and then trend that as it progressively may get worse. Now, some of the problems that can occur inside of the rotor. Well, we just discussed this, cracked or broken rotor bars. Porosity. Porosity in the cast aluminum design. Defective rotor iron. Or lamination damage. And these broken bars or porosity or the problems that can occur create heat or high temperatures and a subsequent loss of torque. So it's important that we monitor the rotor, make sure it's healthy, and that it's operating in a good, stable condition. Now, PDMA, as you can see here with our Emacs, uses a spectral analysis approach, and spectral analysis allows us to take a simple current signal and apply a FFT or fast Fourier transformer algorithm. FFT capability reveals small but very informative frequencies like pole pass frequency. And in this case here we have an X on our pole pass frequency, and you can see PDMA puts in our observe line or our caution line or our severe line. So as the problem gets worse, or if you have a single cracked bar or multiple cracked bars, you'll start to see this pole pass frequency develop more energy and stick out from the baseline or the noise level of the spectrum. We don't want to stop there. We want to utilize every tool available in the Emacs, and we go out to 480 Hertz, which allows us to use our swirl or look at our fifth harmonic. And the fifth harmonic is essentially a phase shift in the air gap flux on the rotor. This creates around the fifth harmonic our pole pass frequencies, and so we monitor for them. We also utilize demodulation, and that essentially filters out our 60 Hertz signal. And what's left behind are mechanical anomalies or mechanical energies in the demodulation spectrum. We can also utilize this for very accurate 2-pole rotor bar analysis. We can use our inrush startup current, which is monitoring the most stressful time of the motor. And for MCE, we look at our rotor influence check. Now, as we discussed, inrush startup, or the most stressful time for a motor, which can see essentially maybe 7 to 10 times the normal full load amps at startup. And in this case here we can see the motor starting up, and as it goes through its startup process it goes to 39 seconds and it basically fails. Well, why did that happen? Well, in this case troubleshooting found out that if we just adjusted the time delay relay another second for a longer start time, and if we went out to 40 seconds, we can see that that motor is now running correctly. But we can also use inrush startup current to monitor a process analysis. So if you have a process that you want to look at for 60 seconds, essentially we're just taking a current sample, and you can monitor that process over that 60 seconds, maybe a motor operated valve or something of that, making sure that the events when they're designed to happen actually do happen based on the current that it's drawing. And you can look at if a motor takes maybe a little bit longer or shorter to start up, that could be also attributed to rotor bar anomalies or load changes. The MCE portion of our MC Emacs uses essentially a graphical, provides us with this rotor influence check, which is a graphical representation of the magnetic coupling between the rotor and the stator. The residual magnetism of the rotor interacts with the high frequency signal applied to the stator. So essentially, what are we doing here? What we're doing is we're taking the rotor, we're applying a high frequency 1200 Hz signal to the stator, developing a field on the stator, and we have the residual field on the rotor. And as we rotate the rotor through this field, and depending on the number of poles, it would either be in 5-degree or 10-degree increments, or less than that if it's a higher number of poles. What we then do is we measure out inductance over that period.